Welcome to the third video tutorial in our series on optimizing transcranial electrical stimulation using software tools. In this video, we will delve into the process of preparing actual patient data for import into Zeffiro Interface. Our comprehensive workflow consists of the following stages, which we will explore step by step. Perform a reconstruction of the cortical surfaces, importing the data into Zeffiro, and generating the finite element mesh. You can find detailed explanations of these steps in dedicated wiki pages and scientific papers, all of which are linked in the video description. In this tutorial, we will provide a concise demonstration of the entire workflow, offering valuable guidance and enabling you to learn from a real-world example. We will consider an imaginary clinical case involving a patient presenting with a pathology which requires the application of TES targeting the left amygdala. The imaging data for this example was obtained from an open dataset. So prepare yourself for an enlightening journey and ensure your hardware is ready for intensive computations as we begin this exciting endeavor. For the initial step, we will utilize a third-party tool named FreeSurfer. FreeSurfer is an open-source software designed for the analysis and processing of brain MRI data. It carries out the intensive task of translating our raw imaging data into detailed brain surfaces. Provided that we have our subject's T1 MRI data at hand and FreeSurfer installed, we can kick things off. The following command, mentioned on the wiki page, will initiate the reconstruction process. Bear in mind that this process can be time-consuming, and its speed mostly depends on the single-core performance of your processor. When it's finished, you will have data that's ready to be put into Zeffiro for visualization and further analysis. Before we continue, let's take a closer look at files that were generated during the reconstruction phase. They contain a set of polygon coordinates that represent the 3D head model. Together, they form surfaces of distinct parts of entire head. To import this data, we'll need to launch the Zeffiro interface. Then, select the Import Data to a new project option and choose the import_segmentation file from the directory we've just explored. The surfaces that we have imported are essentially flat and lack the internal nodes, also known as finite elements, that span the entire volume of the model. Therefore, we need to generate a volumetric mesh of such nodes. This can be done by clicking on the Create Mesh button in the Mesh tool. After the volumetric model is generated, you can inspect it in detail by clicking on Visualize Volume within the Mesh Visualization tool. The process of generating a volumetric mesh may require additional refining of the model. This is crucial to enhance the resolution of the smallest brain regions, and in turn, ensure more accurate simulations. We can assess the accuracy of the amygdala reconstruction by choosing a color with higher contrast and hiding the external cortical structures. As you can notice, we might need to increase the precision for such intricate structures. To enhance the precision of the finite element mesh, navigate to the forward and inverse processing options found in the Settings menu. Our aim here is to increase the model's accuracy at the boundaries between various compartments while preserving their internal nodes. This is because the conductivity within these compartments is uniform, so altering their internal density will not significantly impact our results. Conversely, we will be focusing on the internal region of the amygdala, where increasing the mesh density is beneficial. This approach helps us achieve an optimal balance between accuracy and computational complexity. Keep in mind, an increase in node quantity will extend simulation time, so it's important to find the right balance. Make sure to select the right compartments, tick the refinement checkbox, and hit the Create Mesh button once more. See how it improved the mesh precision on the boundaries of different compartments. The entire process of creating the mesh is comprehensively outlined on the corresponding wiki page, as well as in a dedicated scientific paper. Both of these resources are linked in the video description, and we recommend them for a deeper understanding. At this point, we can save the project. This protects our progress, allowing us to freely explore different parameters without the worry of losing our data due to potential software glitches. And that is all for today. To recap, in this tutorial, we've successfully navigated through several crucial steps to prepare our patient data for TES optimization. Here is a brief overview of what we accomplished. We initiated the process by reconstructing the cortical surfaces and transforming raw MRI data into a detailed 3D format. Next, we imported this data into Zeffiro, the primary tool we'll be using for our optimization process. We then generated a finite element mesh. This provides us with a framework to precisely simulate complex structures of the brain. And finally, we saved our project for future use. We're excited to have you join us on this journey. Until then, keep exploring, keep learning, and we'll see you in the next tutorial.